Hello world, it's Rational Pi. We're back here with our second generic search algorithm video. We're just going to go ahead and get started where we picked off last time, and that's where we start with the NQ. Unfortunately, from the time I made my last video to now, I lost my my Visio spreadsheet and my PowerPoint presentation that has all my information. So I'm going to try to recreate those and insert them into the video as I can. If not, we're just going to kind of look at the code and kind of finish up this video so we can move on. So the NQ, what that does, it adds the cell that you're currently at to the queue itself, or the cell that you're about to approach to the queue itself, so that it knows it's either visited or it needs to visit that node that you're currently at or about to visit. And we're going to go see if in the A* search if there's an NQ, and there is. So this is going to take precedence over the NQ that's in the generic search algorithm. So in the NQ here, it says the current row and the current column that you're at currently is going to equal to the cell, which is the cell. So in this instance, it's talking about the cell or the node that you're at currently. And then it's going to push into the queue the cell applied with the self-heuristic, or the Manhattan heuristic we talked about earlier, row, column, then row and column. So what does that mean? What we just did was we applied now to the cell we're at currently the heuristic, which is the rows away from the goal plus the columns away from the goal, and then we assigned it its row and its column. It's very simple, and it feels like it's kind of recursive because it should already have that information, but if we haven't visited, or if we are at currently these different nodes, then we need to be able to know the cost that we've already approached and that we've already traversed. So that's what that's going to be doing. And again, it's called the Manhattan heuristic. It's the one we're using in this Python code provided to us. And then, if I remember right, it's just going to go straight to DQ. Yep, DQ after that. And basically what that does, it just pops off the latest cell that's on the stack. And let's see if there's any. Yep. And right here, it's just going to say it's what's called heap pop, which means it's going to pop off the heap, just like I just mentioned. Instead of saying stack, for whatever reason, they call it heap. And then it's going to say that the current cell is now going to be popped off the stack. And then it's going to have HRC, which is heuristic row column, and that's what's going to then be applied to the current cell that you're at now. And then it's going to return the row and column so that you know what it is that you need to be dequeuing from the stack. So back up. So that's going to be all of the superseding classes that are in the A* algorithm that we're using in this code. So everything else is just going to be inside the generic search algorithm. And that's why it's important to have a base algorithm that you're going to be based everything on. And then if you need more complexity, you can always come back and create more classes later on that add a little bit more functionality to it, which is exactly what we've done here. So we're going back up here. We're going past the DQ, so we're going to get action. So if we know some places that we could go, and that's in our queue, and we know some backtracking links, so we know the path that we've taken previously, what we're able to return from this one is the next step for the agent to take. So if we're not at the goal, it's going to create a second node, and it's going to add it to the self DQ. So it's going to DQ it from the current stack, and we're going to mark it as our next target, and then it's going to be our new goal. And then we need to see if we can even get there. So we're now going to say the goal that we're at is the next node that we want to approach, which is what we just assigned. And then we need to decide how far it takes to get there and what it means we need to do to get there. So just as I explained in the last video, if it's 1, 0, which means we move to the right 1, it's going to be action 1. Action 2 is where we go up 1. Action 3 is where we go left 1. And action 4 is going down 1. And this is what it does. It just calculates how many rows from the current position to the target position. Usually it's going to be 0. It's either going to be 1 or -1. It can't be anything else. And it uses that information for the rows and columns to decide what action we need to take. And then if it determines that action is invalid, then we try another action. If it decides that's valid, then we use that action. Then we move on to the visit definition right here. I need to stop calling them classes. This is Python. They're called definitions. I'm sorry. I apologize for that. I'm not a big user of Python, obviously. So the visit, all that basically does is the same thing as get action. However, it adds whatever all of the nodes that we visited previously, it adds them to a certain self.visited stack or a list effectively. And what that does is if we ever need to backtrack and we've already visited it, unless we have nowhere else to go, we're probably not going to go back that same way. Unless we know for sure that the total path going this other way is more than the path of going backwards and trying a different path. Self.start is the very first action you're going to be taking in the generic search, and it's going to be the very first thing that the agent's going to be taking. And so we're going to find what's called the observations. Observation 0, as noted right here, is going to be the rows of the agent's current status, and observations 1 is the column of value. Whenever I edited this code for my artificial intelligence class, I created a second observation and I assigned all the nodes pre-made heuristics. That way I knew what the path cost was going to be initially. We had some preconceived knowledge of all of the nodes. That way it was a lot easier to find the path costs. And then we add to the visit our row, our column, and our observations, and then we just decide which action is best, or if there's only one action, find that one action that we can take. Definition act, basically what that means is it selects an action and we take it. In fact, he even has a good explanation here. It chooses an action after receiving the current sensor vector and the instantaneous reward from the previous time step. For the manual A* search, we dequeue our next node and check if we can go there. If we can, we do, and mark the node visited. If we cannot, we have to follow the path to the goal. So basically what it means is we have a full list of visited nodes. Does it make sense for us to go this way, or does it make sense to go this way? And if it makes sense, we move on. If it doesn't, we need to start heading back towards the goal, which that one is the one that works with the self.visited or the definition visited class that we just talked about earlier. Not a class, not a damn class. I need to get that out of my head, and you guys need to help remind me. If I ever make that mistake again, you need to yell at me in the comments. So the definition end, at the end of the episode, we just print final reward and the cumulative fitness from the best path to the path that we found. It's a automatic sequence that is collected during the process of the code, and it will tell us, okay, well, this path may have been the best that you could find. However, there might have been one that's a little bit better, and that's what the fitness decides. If the fitness is 100, then obviously it's 100%. We got it correct. It may only be 90, 95, whatever. The reward I've noticed in the code that was provided to us doesn't really work the way it should, but effectively the reward is the total path cost. And then mark the front, mark target, mark visited, mark path are just markers that are used to find where we've visited, the next path in front of us, and then the path that we've taken previously. And at the very end, if you notice when I ran the simulation before, at the very end it had the white path. That's the one we actually took. That was the best one we could find, and that's what that calculates there as well. So I hope that this made sense. I hope this has been informational for you. I'm trying to get rid of the word I'm still not great at explaining what's going on right now, but I am getting better, I feel. I've been getting some good comments, some good private messages on here that's been giving me some good advice, giving me some good projects moving forward. I did it again. I don't know why I keep doing this. I may just because I have a visitor in the room. This is the first time I've also done it with a visitor in the room, so hey, there you go. But we're approaching 9 minutes, so we're going to end it here. We're done with the generic search algorithm. We're going to start applying what we know now to the MBA conferences project, and I will see you guys in the next video.